Welcome back. You really are a tenacious little bugger if you are pushing through for a third episode of double replacement reactions. There are many, many other types of reactions, so there'll be many, many more of these recordings. I do applaud your enthusiasm, even if it's a veiled attempt at trying to suck up. But in any event, I hope your grades are improving, and I'm happy to continue to help you along. So off we go. Again, these are double replacement net ionic reactions, so we want to get rid of all the spectators. So all ammonium compounds are soluble, and so I don't have to worry too much about that. What I do have to worry about is the fact that this ammonium is in the presence of a base, and it's a strong base because that's a 1A metal. So what I'm really going to do here is have a little bit of a acid-base reaction where I'm going to make ammonia gas. So the question becomes, you can get that 1A metal out of there, but what about that sulfate? Well, if those two got together, indeed, it's still going to be soluble, and the sulfate is not responding as a reactant in this equation. So we have NH4 plus OH minus makes stinky ammonia gas and our good buddy water. So are we balanced? Yes, we are. 5 H's on each side, one N, one N, one O, one O. Total charge on the left 0, total charge on the right 0. We're good to go. So you're going to have to embrace the fact that ammonium and a base is going to lead you to this essential equation. And the question becomes, what about the other players? So when you think about potassium sulfate, we're back to the FOIL method that you learned in algebra. So we're talking about the inside pair of these two critters. So you'd make potassium sulfate, which is soluble, and would just fall right back apart into ions. So a solution of ammonium sulfate, again, is added to a saturated solution of barium hydroxide. Barium hydroxide is actually a strong base also, so you've got to expect this. But now you've got to contemplate as well the barium and the sulfate. So you get your good buddy barium sulfate as a precipitate as well. So everybody plays this time. NH4 plus SO4 2 minus plus Ba2 plus. Why am I writing this ionized or dissociated? Because it is a strong base. 1 and 2A metal hydroxides are strong bases, except for the two little guys at the top of the 2A's. So we're going to indeed make our ammonia and our water from the reaction of this, with the ammonium and the hydroxide. But we're also going to make that favored precipitate BaSO4. You've seen it at least a half a dozen times by now. And I'm not going to promise you that you're through seeing it in the set. So dilute sulfuric acid is added to solid, ooh, good, I don't have to think about that one, calcium fluoride. Calcium is a 2A metal, thus it has a +2 charge, so I need 2 F's since they're -1 each. So dilute sulfuric acid should be written as H plus and SO4 2 minus. If it were concentrated, I would write it together as H2SO4. But it says very clearly it's dilute. And so we have a true double replacement going on. We're going to put this acid on this solid, and it's going to dissolve, and then we're going to switch partners. So we're going to make HF, which is a weak acid. The other hydrohalic acids are actually strong, HCl, HBr, HI, but HF, the little guy, is weak, and you just need to know that. That does not mean it's not dangerous. It will eat the calcium directly out of your bones, and an amputation will be in your future if you ever spill it on yourself. You won't even find it in high school. So CaSO4, because that is like BaSO4's cousin, and it is insoluble. So this is written together not because it's a precipitate, but because it's a weak acid. This is written together because it's a precipitate. All right, now, do we have any balancing to do? I think we do. Yeah. What's going to happen? Oh, it's because of the F. So there's 2 F's over there. I need a 2 there, which forces a 2 there. And I think that's it. Yeah, so now total charge on the left is 0, total charge on the right is 0. We're done. Dilute hydrochloric acid, which is strong, so think H plus, is with a heavy metal bad guy. So normally you would see me cross that chloric out and just write H plus, but I was scanning along to see if I had any of the heavy metal bad guys. So heavy metal bad guy is present, so I cannot cross that out. So what's going to happen here? the nitrate is definitely a spectator, and this time the H plus is a spectator. So think H plus and Cl minus, where I'd make nitric acid, but that's a strong acid, it's going to fall right back apart. So I'm simply going to pick up that halide ion. Now the mercury 1 ion is not this ion. That's not it. I know that's what you want it to be, but mercury's a freak anyway because it's the only liquid metal at room temperature. You can hold gallium and you're hot enough to make it melt into liquid, but at room temperature, mercury's the only freakazoid that does that. So it's diatomic with a 2 plus charge, so that each of the mercury atoms is a +1. That's a give up and memorize moment. It's not something that you just would stumble upon by accident. You'd have to actually have given a brain cell or two off to that concept. So there's my, that's not it. That's it. There's my mercury 1, which really has a 2 plus charge. And that's going to require 2 Cls. And that is going to make a precipitate because halides are soluble except silver, mercury, and lead, the heavy metal bad guys. Haven't seen that in a while. So do we have some balancing to do? Of course we do. I need 2 of these. Already had 2 of those. And so now I got a total of 0 charge on the left to balance out my 0 charge on the right, and all is well. Dilute sulfuric acid is added to a solution of lithium hydrogen carbonate, which this could have also been written as bicarbonate. But however you want to write it, it's HCO3-. So the lithium is a spectator, and that means my sulfur is also, so this is really just H plus here. So H plus, because I would make lithium sulfate, which is soluble, is why I'm knocking that sulfate out of there, plus HCO3- yields H2CO3, which you pause for a moment and go, no, 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 no. H2CO3 is never written that way. It's water and carbon dioxide in an open container. So you can write it the way I did, or you can simply get rid of that, but this is what's going to get your points, knowing that anytime you make carbonic acid, you're going to go directly to water and carbon dioxide. And again, this is the HCO3- ion, the bicarbonate ion, if you prefer. Balanced, total charge on the left, 0, total charge on the right, 0, 2 hydrogens on each side, 1 carbon, total of 3 oxygens on each side, we're good. Dilute hydrochloric acid, okay, I don't see any heavy metal bad guys, so it's safe to do this, and just think about that, is added to a solution of potassium, get that out of there, so 1A metal, sulfite, so H plus SO3, 2-, not sulfate, but sulfite. You have to memorize it's going to make a gas and water. So it's going to make our water. It's also going to make a gas, and the gas it's going to make is where the gas of S and O that does not change the oxidation number on the sulfur. So this sulfur is sitting over here with a +4, so this sulfur has to sit over here with a +4, which means I need 2 -2 oxygens to make that a neutral molecule. I also need to balance this because I have 2 H's right here and I need a 2 there. 3 O's total, 1 S, yes, yes, yes. And total charge on the left is now 0. Total charge on the right is 0. It's all good. Carbon dioxide gas, I don't have to think too hard about that, do I? I don't have to worry about solubility rules. If you tell me it's a gas, I just get to write CO2. Is bubbled through water. Ooh, another easy one. Containing a suspension. Suspension is where you see solid stuff. So that's code for solid. Present. Think about chocolate milk. If you make chocolate milk out of powder or syrup and you let it sit too long, what happens? You get solid chocolate down on the bottom, and that is a suspension. So I get to just write calcium carbonate. Calcium is 2+, carbonate is 2-, so I need 1 of each. But I must know that carbonate is CO3. And what am I going to make? Well, if you're bubbling carbon dioxide through water, that's this little bubbled through water business means you just made carbonic acid. Carbonic acid then is basically being added to chalk. So bubble, bubble, bubbles, and the chalk is going to dissolve. So I'm going to make HCO3-, and I'm going to make Ca2+. because my acid is basically going to dissociate, and the H is going to be attaching to the carbonate ion, freeing up the calcium ion. So are we balanced? No, we're not, because there's two H's over here, so I need two over here. I've got enough carbons, 2 carbons on each side. Let's deal with the O's. 2 plus 1 is 3, plus 3 more is 6. 2 times 3 is 6. That's good. Okay, so balanced total charge. 0 on the left, 2 minuses, 2 pluses, 0 on the right. I think we've got it. I think that's all I needed to do. Excess concentrated sulfuric acid. There it is. Excess concentrated sulfuric acid. That is code for H2SO4 in the molecular form, because 97% of the molecules in the container really do exist as H2SO4. Is added to solid, don't have to think about that either, calcium phosphate. Calcium is a 2+, phosphate is a 3-. It's a 2-3 trick. I need 3 of the 2's and 2 of the 3's. Put acid onto something that is solid, it's going to dissolve. They wouldn't be asking you this stuff if we didn't have an actual reaction take place. So what am I going to form? If I put the calcium and the sulfate together, the question is it soluble or insoluble? Most books would tell you insoluble, or I'm sorry, most books would tell you soluble, but some books would tell you insoluble, so you can write this either way. But when I put the H pluses with the phosphates, I'm going to make phosphoric acid, or I can make HPO4 2-, H2PO4-, or I can go all the way to the molecular weak acid, which is what I'm choosing to do. But there are other possibilities. There's a lot of different ways to get this correct. They're just kind of become a pain to balance. So I'm going to go all the way to the weak acid, H3PO4. If I go to H3PO4, just doing the outsides, now I'm going to do the insides. I can again write CaSO4, or I can ionize these. It just depends. It's up to you and how you want to balance out the equation. I'm trying to see if it makes it simpler to keep it all molecular, which is still legal. So this is one of the trickier ones. I gotta say, this is a trickier one. You don't hurt yourself if you miss this one. All right. So what have I got? I got 3 H's and 2 H's, which is a 2-3 trick in itself. So I need 3 of those and 2 of those. What did that just do? That just caused me to put a 3 over here. And now do I have it? 6 H's on the left, 6 H's on the right. 3 calciums on the left, 3 calciums on the right. 1 sulfate, 1 sulfate. 2 phosphates, 2 phosphates. By George, I think I've got it. And it's 0 and 0 on each side. So again, let me try this again. Why did I write H2SO4 to begin with? Because normally that's a strong acid and you would separate it because of the words excess concentrated. That means it really is the stuff in the jug in the stockroom, which is 97% H2SO4 and only 3% water. And that's added to solid, so no brainer there. Just write the formula for calcium phosphate. +2 - 3, 2-3 trick. To keep this molecular, because if you start ionizing stuff, you're going to get yourself into a bit of a sticky mess with some redox stuff going on, perhaps. If I just keep this the way it is molecularly, it just made it a little easier to balance. But like I said, it is not improper to have written HPO4 2- and Ca2+ and SO4 2-. It just makes your balancing a little trickier and a little uglier, but you can do it. So if you balanced it correctly, you're still going to get a correct answer. All right. Hydrogen sulfide gas, H2S, is bubbled into a solution, so we're really making an acid here, of mercury 2 chloride. So we would make hydrochloric acid, which would promptly fall back apart. So really, I just need the Hg2+. Because mercury 2 is not it's still a liquid metal, but it's not a freak. You're putting this into solution anyway, so I don't want to plant a misconception about that. There's only 2 kinds of mercury in the ionized form, 1 and 2. There's 1. Here's 2. Yeah, they're both 2+ just to annoy you. But this is the freakazoid. That's the one that's diatomic in solution. Alright, so H2S plus Hg, the only thing that can happen here is I make HgS, and since this was a +2 and S is a -2, that's fine. And then realize you're not going to release hydrogen gas. Realize you're going to release 2 H+, because when you bubble hydrogen sulfide gas into a solution of anything, you're going to make an acid. nonmetal gases of hydrogen are going to do that. So let's see what balancing we have to do to get this right. I've got, oh, I put the 2 in here, sorry. 2 of those are necessary. Is that all I need? Total charge on the left plus 2, total charge on the right plus 2. I got 1 mercury on each side. That's it. We're done. Then solutions of zinc sulfate and sodium phosphate are mixed. Out of there. The sulfate. Also, if I made, yeah, I'd make sodium sulfate, so that's out of there. So zinc and phosphate. And we have an easy one, a 2-3 trick. ZnPO4. I need 3 of these and 2 of those. And to balance, I need 3 of these and 2 of those. And I believe it's a done deal. Yes, indeed. Okay, so we're closing in on a finish here, folks. Your endurance is about to be rewarded with the last 3. Solutions of silver nitrate and lithium bromide are mixed. Well, good grief. Got a nitrate and a 1A metal. So Ag plus a heavy metal bad guy, or that's the heavy metal bad guy plus a halogen, halide ion in this case, makes AgBr. And it's balanced. And that's an easy, greasy one. Then we have solutions of manganese sulfate and ammonium sulfide. So they make ammonium sulfate. All ammoniums are soluble, so out of there, out of there. So Mn2 plus S2 minus makes MnS. Also balanced, also easy. Don't overthink them. Excess hydrochloric acid is added to a solution of potassium sulfite. 1A metal, get the chloric out of there. This is just H+. So H+ is added to SO3 2 minus. Are you getting the feeling this one might be important since this is, I don't know, the 4th or 5th time we've done it? What are we going to make? Either give up, memorize it, or stick with the idea that this is a +4. Make the sulfur oxide gas, the SOx, as we usually call them. SOx and NOx, which, by the way, bubbled into water make acid rain. But that's exactly what's going on here, is we're going to make H2O plus SO2, and since this is all happening in solution, it's equally correct to just write H2SO3, which would be sulfurous acid, which is weak, because ites go to us, ates go to X. So this one, if I did it that way, would need 2 of those to be balanced. This one still needs 2 of those to be balanced anyway. So either of these is correct. All right. Well, that concludes this session. On to acid anhydrides, or anhydrides of all sorts. That'll be our next topic. We are now completely finished with double replacement. Hope you found this helpful. See you next time.